Hello ladies and gentlemen, and welcome to this session on analyzing a 3D reinforced concrete frame. In order to start the analysis using Oasis GSA, which we will be using version 9, you can check the version by click on Help and going to the About. As you can see, the Oasis GSA that I'm using is version 9 build 96. You can update or check for any updates available for this software by clicking Check Now. In order to start the project, you can either use this shortcut over there to start a new project, or you can go to File and then click on New. A wizard will appear. The first section of the wizard just asks some references and some information about the project. These are not necessary and is for your own information and reference. Items like job number, job title, subtitle, calculation heading, and or any additional notes can be input here. As they do not affect the analysis, we will keep it blank. So we go to the next section. As I mentioned, this structure will be in 3 dimensions, so the structural type will be space, and the global restraints will be none. That means that all the movements in the X, the Y, and Z, as well as all the rotation along the XX axis, YY axis, and ZZ axis, as default will be allowed, unless we specify it that there will be some restraints or constraints. One of the most important bits of any analysis is the units. So let's check out the units. As default, GSA has different unit types automatically set in it. For example, SI, kilonewton meter, kips feet, kips inch. We are going to work in kilonewton meter, meaning that for large lengths we will be using meter, for small lengths we will be using millimeter, for forces we will be using mainly kilonewtons, for stress we will be using megapascal or newton per meter to the power of 2. You can change these units as well, but we are going to use as default kilonewton meter. We are not going to design the building, we're going to only analyze the building, meaning that we know the properties, the material, and the cross sections and the dimensions of the building. But in case you want to design, you can input the design codes for the building. As you know, for steel, if you're designing it based on Eurocode, you have to select British Standard, Eurocode 1993, and if you want to design concrete, you have to use the British Standard Eurocode 1992. But again, we're not going to design the building, so you can leave them as they are. We will go to the next section. As we're going to define a considerable building in terms of details with lots of columns and beams, the wizard can help us quickly allocate some default material to it. So the first bit is to define the material grade. Our building is reinforced concrete, but in case there will be any steel used in it, we can select a material grade for that as well. For example, I'll just select S275 for the steel. The concrete that I'm going to use is C2530, so from the drop down menu I will select that. As you can see, C2530 is allocated there. For the reinforcement grade, I'll be using a 500A. As you can see, again, GSA has some ready-made library of material. So now that the material are selected, we have to select the sections. Again, you can do this later on during the modeling process, or you can use the wizard in order to do it quicker. Our building is a reinforced concrete building, so all the column sections will be reinforced concrete. All the beam sections will be reinforced concrete as well. All the general sections will be concrete as well, and the slab properties will be concrete as well. You can add details to them as well. For example, if I want to define a specific column, meaning that all of my columns I want to be of a specific section, I can add them here. So the member type will be a generic 1D. The material grade, as we discussed, will be C25. The analysis material, which takes the stress strain behavior curve, will be based on the material grade that I have defined. For example, my section will be a rectangular section. I can name it. I can say column, for example, so I know what I'm dealing with. The depth can be, for example, 500. The width can be about 500 as well. The units are in millimeters. I'll just click OK. I can do the same thing for the beam sections. Again, the member type is a generic 1D. The material grade is the material grade that I have defined. If it's a different one, you can add some additional material as well. But I will keep the C25 for my columns and beams. The analysis material again refers back to the material grade that I defined. So the stress strain behavior will be allocated based on the material grade that I have defined. My beams are rectangular as well. You can have different sections as well. So sometimes beams can be T sections. So you can select a T section. But in our case, we will select a rectangular section. Again, I will name my section. So this time is a beam. The depth, I will take it as 500, while the width, I will take it as 300. The unit is allocated here, so make sure that you pay attention to it. I'll OK it. I can define the slab properties as well. The analysis material is concrete. I'll have concrete slabs. The material grade, as mentioned before, is C25. The property type is a shell. The thickness of my slab is 150 millimeters. And I can mention whether to follow the local axis or the global axis. For now, I'll just say local axis. I'll just OK it. Now that my material is defined and my section is defined, I can either use the wizard to help me allocate the nodes and elements and members, or I can input them manually later on. Because our structure is a big structure and it's a little bit complex, I will be using the properties given by the software in order to define how complex my structure is. So I will say generate data for the selected structural type. I'll click on it. It will ask me what type of structure you're going to use. Is it like a 2D frame, like a portal frame? Is it a truss? Is it a portal frame? Or is it a space frame? We are working and we are designing a 3D reinforced concrete frame. So we are going to work in a space. So I'll select the space frame. So as you can see, the wizard has changed to an orthogonal frame wizard. The units are in terms of meter, so pay attention to this unit generated here, because later on we're going to give some values. I will ask the wizard to generate elements for me. This means the elements will be connecting all the nodes defined. I will ask it also to generate members for me. This means that a cross section will be allocated to that element which is defined. The geometry is defined here. The number of bays which are in X direction, I will say 5. This follows back to the building that I want to define. The number of bay So now we are in the data generation wizard for an orthogonal frame or a space frame. As you can see, it indicates what the length unit is. In this case is meter. So pay attention to this meter, because all of the numbers input from now on will be in terms of meter. The first question is about generating elements. Elements are members which connect two nodes to each other. So we will ask the software to automatically generate the elements as well. So when it generates all the nodes, it will connect them to each other as well. I will also ask it to generate members as well. This means that the cross sections that I define here will be allocated to all of those generated elements. I can also ask it to include the supports. As you know, as default, the supports at the bottom, the ground floor nodes will be fix. So if I click on this, The supports at the bottom will be automatically generated. I will also tell it to include the self-weight, so the software will calculate automatically the dead load according to the material that I use in my beams and columns and slab. And then I can start generating the geometry of the building that I have. This follows the drawings that you have or the building that you want to generate. The first one is the length of the bay in terms of width for X direction, for Y direction, and then the height of each floor. So my bay width in X direction is 5 meters, and the unit follows this. In Y direction, my bay width is about 4 meters. The unit follows this. And the height of each floor in my case is 3 meter point 2 according to this unit. The number of bays that I have in the X direction are just 4. The number of bays that I have in Y direction is just 3. And the number of stories that I have for my building is about 4. As you can see, some sections are defined for columns, for beams in X direction and beams in Y direction. These are based on the sections that we defined previously. As you remember, for the column, we said we have a column with depth of 500 and width of 500. For the beams, we had a beam with depth of 500 and width of 300, so I'll select that. We can give more details regarding each of these. So if I just click on this column, I can generate my column in more details. For example, the first one will ask me the name. I'll keep it as column. The material, I'll say it is concrete. As default, the grade that I have defined in the previous sections will appear. The analysis, again, similarly, I'll just tell it to follow the stress strain curve that I defined for that grade. In order to give details in terms of reinforcement and stuff, you can click on profiles. The column that I have, as we mentioned before, is rectangular. You can define different types of sections. Just pay attention to the unit here. It will be millimeters, and mine is rectangular. There are some ready-made sections in catalog of GSA, but I'm going to define my own section. So I just select rectangular. I'll go to the next section. It will ask me what is the depth and what is the height of my cross section. So as we remember, and the unit is indicated here, it will be in terms of millimeters. You can have a solid or a hollow section, but in my case it's a reinforced concrete solid section, so 500 500. I'll go to the next section. It automatically starts asking me showing me some information about the properties of it, for example the area or the second moment of area in terms of y-axis or z-axis. If they're correct, I'll just click on finish. My section is generated. As you can see, it's a 500 in 500 is a column, and it follows the grade of a concrete material for C2530. I can give more details about it. For example, in terms of how much per ton it will cost, or some environmental attribution. We're not interested in that, so we will leave it. But as my section is a concrete section, I can define some reinforcement for it. So I'll click on reinforcement. In the reinforcement section, I can define the links which resist against the shear, so I'll click on it. The material of my links is 500. The link members that I'll be using are 16 millimeters, and I can say from where to where with what link spacings I'm putting them. I'm putting them as 150 millimeters from 0% of the length of my column to 100% of the length of my column. So link elements or shear reinforcement will of 16 millimeter diameter with a material strength of 500 will be placed from 0% length to 100% length at link spacings of 150 millimeters. I'll just OK it. My links are done. The cover as default is 25 millimeters. You can give some more details about it. Mine will be having a uniform with with a spacing of 25 millimeter from each face. So I can OK it. You can give more details if you want. And I just have to add some reinforcement to it. I can use the templates which GSA already has. So I say add. It has some templates for column, it has some templates for beam, slabs and wall, or ribbed slabs, or other types of slabs. I will be selecting the column. I'll go next. It will ask me how many bars in my columns do I have. I have 4. There will be reinforcement bars, and I'll tell it that all bars are about 25 millimeter and they have uniform diameters. So now this arrangement is allocated to my column section. I'll just click on finish. A cover is shown. It does not show you the reinforcement bars. I'll just OK it. My column is now ready. I have defined the material, the grade of it, the analysis type. I have defined the cross section, which is 500 in 500. I have defined the reinforcement, the cover, and the links. And I'm not interested in the rate or environmental attributes, so I'll just OK it. This one is done. I'll go to beams which are in direction of X. The material of these beams will be concrete. Automatically the software knows that I'm just interested in this type of material. If this is not the type of material for this beam, you can add new material with higher or lower strength as well. The analysis will take the stress strain curve from the grade. I will be defining the cross section of this beam. Again, it is a rectangular cross section. I'll have the units in terms of millimeters. So I'll go next. My beams have depth of 500 millimeters and a width of 300 millimeters. As you can see, the unit is indicated here. Go to the next section. Some properties of the cross section that I just defined are shown here. If you're happy with them, you can click finish. The cross section is shown here, so it's 500 millimeters in 300 millimeters. I now can define the reinforcement for it. The links, I'll again use 16 millimeter diameter links with 500 in terms of material and a spacing of 150. These are just examples. These values might be different in your case, so allocate them according to your structure. The cover in my case will be 25 from all faces as well, 25 millimeter from all faces as a default. I will be adding the reinforcement using the templates that GSA already has. So I just click on add template. This is a beam, so I select the beam arrangement and I'll click next. It will ask me how many reinforcement do I have on top. I'll have 2 reinforcement on top. They are about 20. They are bar reinforcement and they're in just only one row. At bottom, I have 4 reinforcements. They are again bars. They are 25 millimeters in terms of diameter and they're just in one row as well. I'll click next. I don't have any side reinforcement, but if you have, you can allocate their positioning and their number as well as the diameter. So I don't have any side reinforcement, so I'll just keep it as none. There's some allowances for the transfers. We'll keep these as none. And I'll just click finish. The cover is shown, the reinforcement do not appear. So this is my beam section in the X direction. I'll just click it OK. So 500 millimeters in 300 millimeters. I have defined the material. I have defined the cross section, which is 500 in 300, and I have defined the reinforcement. I'm not currently interested in the environmental attributes, as well as I'm not going to give any pound values per ton for this section. So I just click OK. my beam is ready as well in X direction, I will select the beams in Y as well. In some cases, your beam in your weaker or stronger direction is different than the other direction, so the wizard will help you with that. In my case, my beams in X and Y are the same, so I can select the same thing that I just defined, as you can see. So this one and this one are the same, while the column is a different section, is 500 in 500. So now I'm asking the software to generate my base in X direction and in Y direction according to the number and the length that I have given. Also, it will generate the number of stories and their heights. It will generate the elements, meaning connects the nodes together. It will generate members, meaning that it will allocate these sections that I have defined to the elements which generates. It will include the supports at the ground floor. They will be all fixed, as well as it will include the self-weight of the sections. So I'll click next. And as soon as I click finish, the software will generate my model. As you can see, it has generated it. This is the XY view. This is the general workspace of GSA. I'll just full screen this tab. I can zoom out, and as soon as I click and drag, you can see my structure. I'm just using the click to rotate my model. As you can see, this is the general axis. It's in 3D dimension. Z goes from bottom to top. X is in this direction, the red line, and Y is in this direction, following the the green line. It has 1, 2, 3, 4 bays in X direction, with a length of 5 meter, 5 meter, 5 meter. Each of these grids represents 1 meter. As you can see, 1, 2, 3, 4, 5, meaning 5 meter. It has 1, 2, 3 bays in Y direction, 1, 2, 3, 4, each of them being 4 meter. And it has 1, 2, 3, 4 floors, each of them being 3.2 meter. The units are always shown here, so pay attention to them. The design codes are shown here as well, but we are not going to design this building, we're just going to analyze this building. The orientation views are shown here, so you can select different orientation. This is the plan view. This is the X elevation. This is the Y elevation. It also shows the location of the axis as well. So as you can see, this is the height in Z direction, and this is X. And this is one of the most commonly used views, the isometric view. You can use these options to zoom and rotate. You can use these options to select nodes, or select any of the elements or a group of elements. We will be later on using these options to select nodes or elements. You can deactivate the grid from here. In some views, you might need to deactivate it for a better visual. The labels are all here. You can activate the labels for node dots. As you can see, the node dots appear. You can activate the label nodes in terms of ID. As you can see, the node IDs appear. It starts from 1, 2, 3, 4, 5. It goes all the way to node ID number 100. I can activate the restraints here. As you can see, we ask the software to automatically restrain all of the nodes at the bottom. These nodes are now fixed, meaning no movement in X direction, no movement in Y direction, no movement in Z direction, also no rotation along XX, YY, and ZZ axis. You can also see the ID of the elements. The ID of the elements are shown in the middle of the element with a blue color, while the node IDs are shown beside the node in black color. You can also see the label of the section. the orientation of the label is shown. As you can see, the beams have this orientation while the columns have this orientation. These are the diagrams which, after we finish the analysis, we can see different diagrams in terms of loads applied, in terms of displacement, in terms of reaction, in terms of axial forces, in terms of shear forces, and in terms of bending moments. These are the contours. Similarly to the diagrams, you can see the displacement contours, the reaction contours, the axial force contours, the shear force contours, and the bending moment contours. These are the graphical interfaces, graphical options, as you call it. The first option is shrink. As you can see, it disconnects the connection, the joint where the beams and columns connect for better visual. I can select this, which indicates the section. As you can see, all of the sections that I have defined are now allocated to the elements, and I'm just using this option to see whether they're correct or not. As you remember, the columns have 500 in 500, while all of the beams are 300 in 500. So if I use the shrink, I can see the cross sections of my columns as well as my beams and their orientation. Now that I'm happy with my model, I just have to define the rigid diaphragms. In order to do the rigid diaphragm, I have to select a master node for each of the floors. In order to do that, you have to see the node numbers and allocate a master node for each floor in the XY plane. So for each floor, I will select one of these nodes. So I'm going to write down the number of these nodes: 25, 45, 65, and 85. For each floor, I'm selecting one master node. Now I have to make a group of all of the nodes in that floor. To do this easily, I'll just change the elevation. So I'm now looking in the Y elevation view, meaning this direction is X, this direction is Z, my first floor, second floor, third floor, and fourth floor. I will select all of the nodes in each of these floors and I will group them together. In order to select the nodes, you have to use this option, select nodes. Just activate it. Drag and take the box, the selection box, around all of the nodes that I want to be in similar group. I'll just leave the mouse. All of those are selected. I'll right click somewhere and I'll go to the option Save Selection as List. It will ask me to name this list. I'll call it First Floor Nodes. I'll make sure that I've taken note of that as well, so later on if you want to call it, I have to call it exactly with the same name. So first floor nodes are selected now. I'll remove my selection by just clicking on a white bit. I'll select the rest in the second floor. As you can see, all of the nodes in that floor are selected. To make sure that those nodes are selected, you can view it in different angles. As you can see, all of the nodes in the second floor are now selected. So I'll go back to my previous view. I'll just right click and I select Save Selection as List. So I will use the same formatting that I used for the previous nodes. As you can see the previous one as well here. I will call these second floor nodes. I'll OK it. I'll click somewhere to deselect them. I'll select all of the nodes in the third floor now. In order to make sure that those nodes are selected, I can have another view. In the isometric view, I can see that all of the nodes in the third floor have been selected and they're indicated with a pink color. I'll go back to my previous view. I right click and I say save selection as list. Again, I will use the same format that I have been using for other floors. This is the third floor, so I'll just change the name to third floor nodes and I'll OK it. Those nodes are now in the third floor nodes group. I'll just click somewhere and I'll select the last floor nodes. I have selected them. I'll just go to another view to make sure that they have been selected. As you can see, all of the nodes on the fourth floor have been selected. I'll just go back to my previous view. I right click and I say save selection as list. I'll say node. Sorry, I have to follow the same format that I have. So this would be the fourth floor nodes. I'll OK it. I'll just click somewhere. Go back to my view. Now that I have all of the nodes in as a group, I can define the constraints. So in order to do that, you have to go to the Explorer, the Output Explorer. This Output Explorer now should be changed to Data Explorer. We have not analyzed yet, so the results will be in Output. We will define our model all in Data Explorer. So I'll select that Data Explorer tab. I'll go to Constraints. I'll double click on it. And I'll go to General Restraints. To do so, I'll go to Data Explorer, I'll go to Constraints, I'll double click it so the menu opens. I'll go to Rigid Constraints. I want to define a rigid diaphragm, so I'll go to Rigid Constraints. I double click on it, a table opens. Generally, GSA works based on tables in order to define different inputs. You can either copy paste from Excel or a spreadsheet or text, but the easiest way is to use the wizard again. So in order to activate the wizard, you go to the first row, which is empty, to the first column as well, and you just double click. As you can see, a menu is opened. For the first one, I'll be naming the first floor. So let's call it first floor. The stage list is all. The nodes, as you can see, a list appears here. You can either name them one by one, or as we did them in groups, it's easier to just select the list of nodes. And I have to give the master node. This master node is one of the nodes that we took notes previously in the same floor. In this case, for the first floor, node number 25 was my master node. In terms of linkage, I want them to have the same rigid diaphragm as the XY plane. So I'll just select XY plane. I have to rename it again. I'll call it first floor. And the master node as well, 25. And I'll just click on OK. The first rigid has been defined. I'll do the same thing for the second and the third and the fourth one using the wizard. So again, I select the linkage, which is XY plane. I'll call it the second floor. The stage is all. The nodes are the second floor. The master node that I selected, which is one of the nodes in the second floor, was 45. I'll just OK it. As you can see, the type of linkage is shown here, XY plane. The master node will be 25 or 45 depending on which floor I have been selecting the nodes from. I'll do the third one. Again, I'll first define the XY plane as my linkage. I'll name it. I'll name this one third floor. It's all stage list. The node numbers are the third floor nodes. And the master node among those floor nodes is 65. I'll just click OK. You can see another one is added. I'll do the fourth one as well. The linkage is in XY plane. I'll call it the fourth floor. Stages all. Nodes are the fourth floor nodes. My master in that floor is 85. I'll just OK it. I have defined my rigid constraints. As you can see, 4 options has been defined. That's why in rigid constraints, as you can see, it doesn't show the file as blank anymore, and 4 numbers have been added. In order to make sure that these are correct, I'll go back to one of the views, for example, the isometric view, and I can ask, I'll take the rotation option, and I can ask the software using this label and displace method to demonstrate me the rigid constraints. If I click on it and I'll just say apply, as you can see, all of the nodes in each floor have been connected to the master node that I have selected. Number 25 for the first floor, 45 for the second floors, 55, 65 for the third floor, and 85 for the fourth floor. And it shows me the rigidity in terms of XY, meaning in planes of X and Y, it will be rigid and all of these nodes will be working together. I can OK this and just rotate to make sure that the rigid diaphragms are applied. As you can see, they're working together. So all of these nodes are connected to them. I can reset my view by clicking on this. As you can see, reset display. And I get my own normal frame. If you can see here, there's a list of nodes. If I double click on it, the list of all of my nodes appear. As we discussed, we have about 100 nodes. You can either edit them in terms of X coordinate, Y coordinate, or Z coordinate. All of my elements are defined here as well. As you can see, it shows 204, meaning 204 elements are defined. All of them are connecting each of these nodes together. And also, they're all type beam, meaning they take shear and moment. If they are trusses, you have to select the bar element type. And the members have been selected as well. In this case, the beams and the columns cross sections that I have been defined are allocated to each of those elements that we have. As you can see, again, a node is indicated and the beams and columns are defined. You can see the material which have been defined here as well. So a steel material is defined, S275, and I only have defined one type of concrete, the C2530. These have been all defined previously using the wizard. So the wizard helped us fill in these forms. Otherwise, you had to do this one by one. I have also defined the reinforcement. If you remember, I had selected a reinforcement of 500, which is also coming here. In order to see the cross sections, you have to go to the properties. Again, you can see one of the menus has 4 items in it. If I click on it, I have my column and I have my other beams. So these two, this one and this one, were some of the default ones, which I didn't use it at the end. I just defined it in the beginning. But if you remember, I defined a proper column with all the reinforcement and all the covers and stuff, and I called it column. And I also just defined one type of beam, calling it X, but I applied it to both direction of X and Y, which this can be seen here. As you can see, all of the beams are just beam X. So if you like, you can delete these because they're not getting allocated to any of the members. Going back to our isometric view. Now, my nodes are defined, my elements are defined, my members are defined, my rigid diaphragms for each floor is defined, my supports at the bottom are fixed as well. The only thing left is to define the loading cases, the dead load, the live load, the snow load, the wind load or the earthquake load, and just start the analysis. The software is automatically considering the dead load of the sections as I have defined it. So if I go to the loading in the Data Explorer, a load case has already been defined. That's why this spreadsheet shows full. If I open it, a dead load has already been defined. If you have a live load, an earthquake load, or a wind load, you have to define it using the wizard over here. So let's define a live load, for example. I'll just double click on here to open the wizard. I'll call it live load. The type is live. As you can see, different types of loading exist. For example, earthquake, snow, wind, or live. I'll select live. The source will be 1 and the direction is Z. This direction does not matter because later on that you give a value to this live load, you can select the actual direction for it. I'll just click OK. I am actually going to define a wind load as well, so I'll just double click on it. I'll call it wind load. The type will be a wind load, the source will be 1, and the direction again doesn't matter. I just click OK. So 3 load cases have been defined. Now, depending on whether you want to apply these loads to the beams or the columns or to the nodes, you can select the type of loading that you want to apply. Now, in order to apply, for example, the live loads to the beams, I have to make and create a group of beams for each floor, similar to what we did with the nodes. So I'll go back to one of my views. For example, the Y elevation, meaning this is the Z axis and this are the elements in the X axis. I need to select all of my beams. To do so, I'll use the tool which is for selecting elements. Just activate it, select all of my beams. If you hold Control on your keyboard, you can add more elements to it as well. So I select the 4th floor elements. I can see what I have selected by using the isometric one. As you can see, all the beams in X and Y direction in the 4th floor has been selected. I'll just group them by right clicking and saying save selection as list. I'll call them 4th floor beams. I click OK. I do the same thing for the 3rd floor and the 2nd floor. So I select them, right click, save selection as list. I'll call them the 3rd floor beams. Last time in terms of nodes, we selected from the bottom floor. Now we're going from top to bottom, really doesn't matter. Now I'm selecting all of the elements using this tool of selecting elements in the 2nd floor. I just right click and say save selection as list. I'll try to follow the same formatting, so I'll just call it second floor. Now I select all of the beams in the first floor. I can check it by changing the view. As you can see, all the beams in X and Y direction are selected. I just right click and say save selected as list, and I'll just follow the same format, but this time I call them first floor. Just OK it. Now that I have a list of my beams, I can simply apply the beam loadings, for example the live load, to them. I just double click on beam loading. I want to apply the beam load, so I just double click on it. A table opens. I will be using the wizard to define it. I will open the wizard. I'll name it first floor live load. Let's keep the beam list as none. We will define it later. My load case is live load. It's a uniform loading. It will be in Z direction, meaning it will go from top to bottom following the global axis that we have. The global axis is the tiny axis that is always shown in one of my workspace views, and the value in this case will be 5. However, I will put a negative behind it, indicating that although the direction of my Z is going from bottom to top and is positive, I want it to go from top to bottom, meaning in the direction of gravity to the center of the earth. That's why I'll put a negative behind it, so it goes from top to bottom. I'll click OK. Now that is done, I can select the beam list that I have. This will be for the first floor. I can, as these are like tables, I can copy paste them. So I'll select that one that I want. I can say copy, and I can paste it in the next row. I can paste it again. As we have 4, I'll just continuously paste. The only thing that I'm changing is the beam list. So second floor, third floor, and fourth floor. All of them have a value of -5. They're in the Z direction. They follow the global axis. That's why I put -5, meaning the loading is toward the gravity. And they're uniformly loaded. They're all load cases live, live, live. If I go back to one of my perspectives, this is my frame. I can tell it to show me the loadings which are applied by selecting this all load diagrams. Currently it's showing me the dead loads. As you can see, load case 1, dead load. I can select live load as well. As you can see, the live loads are applied for the second floor, the third floor, and the fourth floor. If I go back to my beam loading, -5 should be applied to the fourth floor as well. So hopefully if I go back, yes, the fourth floor is applied as well. In order to see the value of these loadings, you can use this option over here, annotation. As long as you select it and activate it, and you select the arrows that you want the value to be shown, it will show you the values. As you can see, they're all -5, indicating that they're going from top to bottom following this global axis over here. If the number of decimals is too much, you can reduce them using these options. So I will decrease the decimal, so it's -5. You can check out the dead loads as well. These are the dead loads. I can tell it to show me all of the dead loads. As you can see, -4 is indicated for all of the beams, and -6 is indicated for the columns. The dead loads will be for both columns and beams, while the live load were just applied to the beams. This loading again depends on your situation, so you can select or list all the beams in the X direction or all the beams in the Y direction using different views as well. So as soon as you group those beams, you can apply specific values and specific type of loading to them, from trapezoidal loading through triangular loading to point load to rectangular loading. For example, I'm going to apply some wind loads to all of the columns in this side. In order to do so, I'll just deactivate the loading. I'll select one of the views that I have. So I'll want to apply the loads to the columns over here. So all of the columns in this side. So I have to select them. So I select the elements using the Select Elements tool. As you can see, all of those beams and columns have been selected. I will right click. I have to select them again. I will right click and I click as Save Selection as List. I'll just call this X side. Yeah, the other beams are here as well, but this is a combination of columns and beams. I just want to apply one sample wind load. So I just click OK. Those are now over there. I will again define a beam load. So I'll go back to my beam loading. I can copy paste the one that I had before. I will change the fourth floor to X side. I will open the wizard. I know that this is my wind load, so I'll just say wind. I'll change the name to wind load. I do select the load case in terms of wind load. It will be a uniform loading as well, or you can select a trilinear loading by giving the positioning from what value it goes to what value. I can do this as well. So I'll put 2 kilonewtons per meter at the 100% and a value of 0 in the beginning. The direction in this case will be in X direction. If I click OK, and I'll go back to one of my views, I activate the load diagrams and I'll select the wind load. You can see that the arrows are indicating the loading. Of -2. However, I have selected the positive direction. I have to select the negative direction. So if I double click on it, I have to select the positive direction. I'll say OK. Now this is in the positive direction. So if I go back to my view, you can see there are like 2, 2, 2. So it goes from 0 to 2, 0 to 2, 0 to 2. There are triangular loadings. I can select a uniform loading as well. For example, again by editing that, I can say give me a uniform loading. So it will be only a value of 2, for example. I'll click OK. I'll go back to the view. And as you can see now, it's a uniform loading. I will keep it as it is and I will start the analysis with this kind of loading. Now, going back to load cases, you can see that I have load case 1, load case 2, and load case 3. I'll be using these load cases in order to define load combinations. To define load combinations, you go to tasks and cases. If I double click on it, I can define combination cases. I'll double click on combination cases. I'll open the first one. And it asks me to refer back to the loading cases that I have already defined. So 1 will be the first loading, which was dead load, will be represented by A1. So I'll say A1 is my dead load. I'll just OK it. I can define another one, and I can call it live load, and it is A2. I'll just OK it. And I can define another one, and I can call it A3, wind load, which is actually described with A3, and I'll save it. Now I'm referring each of these load combinations to the late cases that I have. As you can see, A1, A2, and A3. As soon as I have these, I can combine these load cases again. So now I can mix them. So if I open a new one, I can say I want 1.35 dead load as in the case here, plus 1.5 live load. So 1.35 times C1, which is only dead load, plus 1.5 C2. You can also use A1 and A2. And this will be 1.35 dead load plus 1.5 live load. I'll OK it. Has the formulation there as well. I'll define another one. This one will be only dead load plus live load. So it will be dead load plus live load. I'll just say OK. I'll do a wind load as well. So this one will be dead load plus live load plus 0.3 times wind load. This depends on the load combination that you're going to define from the code. So it will be 1.35 dead load, which is C1, plus 1.5 C2, sorry, will be C1 plus C2 plus 0.3 times C3, which is the wind load. I'll just OK it, and it has defined the loadings. So these loading combinations will be automatically calculated as soon as the analysis is finished. I'll go to the analysis task. The analysis can be started here, or you can go to the one of the views and just simply use one of these shortcuts over here. I'll just reset the view so nothing is shown. As soon as you go to this analysis shortcut, which has a symbol of summation, and you click on it, the model will be analyzed. If there is any errors or warnings, it will be indicated here. As you can see, no errors is shown or no warning is shown. It will give you some general information about your model. So it has 100 active nodes, 204 active elements, 3 analysis cases, 252 degrees of freedom, and some other information. It will also indicate how long it took for the calculations. As you can see, it was pretty quick, and it was all in terms of milliseconds. The more complex your building is, this analysis might take longer. In order to see the results, you go back to one of the views, for example, isometric view. The cases will be indicated here. As you can see, I have my default load cases, so case 1, case 2, case 3, as well as loading combinations, which as I defined them, the first one was dead load, live load, wind load, the first, second, and third. Then I had 1.35 dead load plus 1.5 live load, dead load plus live load, dead load plus live load plus 0.3 times the wind load. These should be defined based on the code that you're going to use as well. Now, let's start with the reactions. For example, in order to see the reactions resulted from those loadings, I can select this diagram. A reaction is shown at each of the members at the bottom, as you can see. In this case, we are in the wind loading type, so if the wind was applied in this direction, these at the end are resisting more. But if I go to the combination dead load plus live load, as you can see, most of the reactions are in this direction. You can reduce the size of these by using these options, or you can modify them. In order to see the values of these reactions, you can use the annotation option. So if you activate the annotation option and you select the ones that you want to see the values, a value is shown beside them. The units of these are in terms of kilonewtons, as you can see is shown over here as well. Again, the values of the loading that we selected are just for an example. They're not realistic. So these loadings might be a little bit too high. So if you design this building, your sections might be much bigger. I can see the actual forces diagram by clicking on this option. As you can see, the actual forces for each of the columns is shown. These are under this loading case. If I select another loading case, as you can see, as I'm using the ultimate limit state values, the actual forces increases. I can also use different combination. Let's include the wind as well, or let's purely just include the wind. In order to see values, you just select the annotation, and each of them will be shown in terms of the units which you have been selecting. In this case is kilonewtons. Let's see the shear force diagrams. This is the shear force diagram under the wind loading. As expected, these columns are having more shear. I can change the combination to just ultimate limit state of dead load plus live load. As you can see, the diagrams are all inside each other, so it's very hard to see. This is the place that you can use the shrink option to have a better visuals, as well as you can reduce the size of the diagrams to have a better demonstration. So these are the shear diagrams for each of the beams and the columns. In order to see values, you can select the annotation and just select the values that you want, the elements that you want the value to be represented. You can do the same thing with the moment diagram. Again, if you want to see the values, you can just select them, or you can select them all, or you can change the views. You can have them as the actual sections while you're showing the diagrams as well. You can also ask the software to show you these results in terms of contours. For example, if I deactivate this, I'll just tell it to show me the contours for the bending moment. As you can see, a legend comes up. Negative moment in terms of kilonewton meter, positive moment in terms of kilonewton meter, 30 is the maximum, minus 25 being the minimum. As you can see, for each of the beams and the columns, a moment contour is shown. The same thing applies for shear. And the same thing applies for the actual load. Again, remember, these diagrams are for the case C4, 1.35 dead load plus 1.5 live load. If I change the case combination, other results will appear. For example, the wind load, or the dead load plus live load plus the wind load for the shear. You can also add some combined cases later on as well. For example, I can say, give me the maximum in terms of all of these guys. For example, an envelope. So if I go back, I can see an envelope. See the diagram as well. I can reset the view. I'll just see the moment. This is the moment envelope, so it indicates the maximum of the values that you had, so the combination of all of these cases, and it will just show the maximums in terms of moment. So each of these maximums can come from one of the load cases, either from the dead load, the live load, the wind load, or the combinations of 1.35 dead load plus live load, or the other ones with the wind. Beside these, you can see the deformed shape of the building under different loading combinations. So for example, if I select the ultimate limit state loading combination, and I'll just click on this, the deformed image, it shows me how the building is expected to deform. As I was expecting, because the loading is just in the gravity direction, the building goes down. I can see the values of these as well by clicking on the display diagram. And you can see the values by using that tool. Remember, the values over here are in terms of meters. A more realistic view of your deformed shape. You can increase the scaling or decrease the scaling, or just go and rescale it to the original. You can extract all of the results that we discussed as well in the Output Explorer. So if I click on Output Explorer, a menu opens. You can see global results of your building, for example, in terms of total loads and reactions under different loading combinations. As you can see, A1 is the dead load, A2 is the live load, A3 was the wind load, and then the load cases that we defined. Again, we defined the dead load, a live load, a wind load, and then later on we combine them. Or accordingly other results, depending on whether you're looking for the elements, the members, or the node results. So that is it for analyzing a reinforced concrete 3D frame using Oasis GSA version 9. Thank you very much.